This is a short video to talk about impulse and change in momentum and come up with some examples on some different ways in which impulse can be delivered. We start off with the impulse momentum relationship. On the left-hand side of the equation is defined as impulse. And the right-hand side is change in momentum. When Isaac Newton first composed the second law in the Principia, this is actually what he proposed. It's later when we added this, when we divide both sides by delta t and specifically identified this concept called force, where delta v over delta t is acceleration. So recognizing that momentum is a product of both how fast something moves and what its mass is, if we check out the units for this, they're actually compatible. So kilograms meters per second on the right-hand side of the equation, and then Newton seconds on the other side of the equation. And usually when collisions happen, the force changes with time, and we might call this a force profile. So the area under the curve, if this is plotting force as a function of time, is impulse. Will equal a change in momentum. But there are different ways that you can do that. You can deliver the same impulse with a short amount of time and a high force, or a longer amount of time and a softer force. Because the peak of this profile is what we would typically call impact. So if we're trying to do things safely, like drop an egg on the floor but use a pillow, or in cars, seat belts, airbags, crumple zones on the front of the car, all designed to increase the time over which this impulse is going to occur. For instance, in a collision, if an unfortunate event happens and we have a case where a car is traveling at 40 miles an hour and suddenly is brought to a stop, well, everything inside the car is still going to be moving at 40 miles an hour, and a passenger could collide with an airbag or a seatbelt or both, or heaven forbid, the dashboard. So the same impulse is going to be delivered regardless. But seatbelts plus airbags are actually going to extend that time, which means that the impulse can be delivered over a wider time, which reduces the force of impact. But sometimes instead we do actually want to break something. So think about a jackhammer. That pop, pop, pop that you hear is a really sharp impulse where the delta t is really small, and as a result, we have a very big impact. So let's take a look at these three examples. We have a bowling ball, a basketball, and BB for basketball, and then a TV BB, Tom Brady basketball, because it's underinflated. Anyway, masses are listed here. And then we assume that the initial velocity for all of them is going to be equal to 5 meters per second in a downward direction. And if we're keeping track by using pluses and minuses, so that would be a -5. And then if a bowling ball rebounds with a speed of 3 meters per second, here's how we calculate the impact force. We need to know the time of the impact. So say 10 milliseconds, very sharp impact. And so that's 0.01 seconds. And then m delta v would be mass 5 times the new velocity, which is 3, subtract the old velocity, which was -5, and subtracting the negative number is a positive number. So this is 8 for delta v, and 5 times 8 is 40. Notice how bouncing is a big change in momentum because the velocity reverses direction. Now we can take that impulse and we can divide it by delta t. So dividing by 0.01 is the same as multiplying by 100. So, is that right? Yes. So 40 times 100 is 4,000. Good. Here's a basketball that doesn't bounce perfectly, but we have a final velocity of 4 minus -5, so that's 9 times 0.3, 2.7 divided by 100 milliseconds because the basketball is softer than a bowling ball is. And we get 27. And then here we compare these two numbers. The basketball is underinflated, so that means the time of impact is longer, and also it doesn't rebound as much. So even though these two have the same mass, they don't have the same impulse. So the bouncing delivers a bigger impulse and therefore a bigger change of momentum. And therefore that impact force is only 7.5. So a couple of key takeaways. There's the role of time in delivering an impulse. And then also this more subtle point, which is that rebounding actually requires a bigger change in velocity than just simply coming to a stop.